Greetings, young physicists. This is Miss Minhares coming to you through a top secret time portal from the year 2076. Can you believe it? Thanks to the groundbreaking work of scientists who applied the very principles we're studying in our class, time communication from the future is now possible. And guess what? It all started with a deep understanding of momentum, impulse, and IFF charts. Today, we're going to explore how to solve problems using momentum bar charts. And you might be thinking, but teacher, how do we really know you're really from the future? I'm from the future where I already saw proof that you learned how to do this. So I already know that this video is going to be really successful and that you're going to be really successful at learning these new concepts. So pay attention. I'm going to go through the first few examples through these videos, starting with number one. Now, number one might be a throwback to the past because we've seen this little man, this little dude riding the elevator before when we studied forces. And now we're going to look at a similar situation, but see if IFF charts or IF charts can help us solve for something that is unknown. Okay. So as any good first step for any problem solving is reading the problem very carefully and determining what information is being given. It says a 50-kilogram person rides an elevator upward. The elevator is pushing on the person, causing a constant net force of 400 newtons. How fast is the person in the elevator going after 2.5 seconds? Using an IFF chart, we would first label the mass of the person, and we can assume that the person starts from rest. Next, we would label the force acting on this person, and we would label the time or the number of seconds that force is being applied. Since this is going to make a box in the impulse graph, we can write a number inside of the box to represent the amount of impulse, which also means change in momentum. 400 times 2.5 is 1,000. And then in the final if chart, we would again label the mass. And what is unknown is how fast. So we're trying to find out how fast the person is going. So when we took our notes, there's one big idea that I wanted you all to remember. And that is the key to solving any IFF chart is to know that the area of the first graph plus the area of the second graph always has to equal the area of the last graph. So in the last graph, we should have a box that has an area of 1,000 kilogram meters per second squared. So the initial momentum plus the change in momentum has to equal the final momentum. Well, how can I make sure that this momentum here adds up to or ends up multiplying to 1,000 if the mass is 50? Well, the momentum is equal to mass times velocity. 1,000 equals the 50 times the velocity. Divide both sides by 50. So here we're using math to find out what this number needs to be so that when we multiply it with 50, it gives us 1,000. The answer there is 20 meters per second. But Ms. Minhares, how'd you get 20 meters per second? Again, we had to find a number. Let's make that number V, or for now the letter V, that when we multiply it by 50 is going to give us 1,000. That is because the area is equal to mass times velocity, where mass in this case is 50 for the person, and velocity is what we're trying to find. So the answer has to be 20 meters per second. Good luck on the next level. Bye.